Good afternoon. Thank you for the invitation. I'd like to point out, first of all, I'm a fraud. I'm not a biologist. What? Oh, it's been so, yes. I may be a bit paleo, but that's because I was a physician for 30 years at the Queen Elizabeth Hospital, and then I was involved with a spin-out company, and that allowed great latitude when it came to retirement, because I've used some of the funds from selling it to assuage my carbon guilt. We're all guilty of being carbon emitters. Students amongst you might be 13 tonnes a year. The government says we're about 5 tonnes a year per capita, but that's not true because we import carbon dioxide embedded in cars from Germany or cameras from Japan. New professors amongst you may be 30 tonnes a year because you're going abroad, you're travelling and talking at conferences. I might be 50 tonnes a year because I've done my fair share of travelling. So when I retired with my wife Barbara, who's sitting at the back, we decided we'd try and offset some of this carbon guilt. And it also relates to a wood stove we had at home, wood stoves in Birmingham, illegally burning timber in a CO2-free environment. But we burn probably 20 tonnes a year. And so I wanted to offset that. And to do that, we thought we've got to plant some trees. And it said that 1 hectare of land will absorb about 10 tonnes per year. So I needed perhaps 2 hectares or 3 hectares, cover my wife as well, and perhaps some children, 8 hectares a year. And as I was Googling, thinking I'll perhaps buy 4 or 5 hectares, I pressed the wrong nought, and we ended up with 400 hectares. And that is Norbury Park. And so in Norbury Park, in this 400 hectares, well, a bit more than that, I don't like to tell you exactly how much it is for embarrassment reasons, but it's planted with a couple of 100 hectares of woodland. And so I thought, well, by growing these woods, perhaps thinning them out, allowing them to expand well, I could offset 1,000 tonnes of CO2 a year. And and that would offset 1,000 tonnes would be 10 years of my life, 10 years of carbon emissions. But the Forestry Commission, much to my horror, all had already claimed this carbon offset. They'd been involved with planting the trees. They'd subsidised the tree planting, which went all the way back to 1840, well, before the Forestry, 1840, when the first Lord Lichfield had planted these trees that are now visible in the BIFoR face rings. So I thought, well, we'll start again. We'll plant on some of the arable land. The Norbury is at the terminal glaciation zone of the last ice age. It's a very variable land, very variable arable land. Some of it's poor, so we decided we would plant a couple of 100 hectares of new land onto new trees onto the rather poor land that was available. And that became the start of the the Norbury plantations. And this shows an early stage. We plant at 1,000 trees per acre, 2,500 per hectare. And we decided we would plant about 70 acres per year for 5 years to get this full carbon offset of 1,000 tonnes per year outside the Forestry Commission. So our target was about perhaps 2,000 tonnes storage per year. That's the aim of the lecture, is to explain how we got there or how we tried to get there and how well we achieved it. And the forestry advisors, I know nothing about. I know a tree is big and it's got leaves at the top, but I know very little more about it than that. And our tree advisors, our consultants, said, what tree would you like to plant? So I said, I've no idea. This was 13 years back. Perhaps you can give us some advice. He said, well, you can plant conifers or you can plant broadleaves, blah, blah. And there's about 30 different sorts in England that you can plant, in Britain that you can plant. I said, well, I've no idea. Plant them all in a nice big mixture, and that decision can be put off for a few years when I've done some reading. So sorry, it's slightly out of focus. I'm slightly out of focus. We planted these trees, and we found that actually they grew quite well. And by year 7, the forester said, well, I think we need to thin them out a bit. They've grown really well. The canopy is closed, and we want to get access to the trees that we want to keep in this mixture of 30 different species. And so we cut racks amongst them. So they were done in straight lines. It's much easier to plant trees with a tractor, pulling a split plough, which you can pop the trees in. And if we took out 1 in 7 rows, then we'd have access to 6 rows, 3 on each side, and we could examine the trees and decide which ones we wanted to keep. So having done that, we realized that some trees were growing rather quickly. Many trees were growing rather quickly. And people visited the site from the Forestry Commission to see how our planting had gone on. And they said, well, these trees are growing extremely quickly. So that led to thinking, well, maybe the mixture has had some enhancing effect on the global growth of these woodlands. It also led us to think about, well, some trees we want to keep that are growing particularly quickly, we want to enhance their growth rates. And there's a policy in France of when they grow oak trees, English oak trees, of course, or perhaps we grow French oak trees. I'm never quite sure about that. We wanted to select the winners, and we wanted to look after them. And the French system is you have a halo thinning around the tree, so the canopy is exposed to full sunlight. And of course, it grows better. The more leaf surface area there is, the faster it grows. But we didn't quite want to do that, because then if we halo thinned it, taking all the trees out that were competing with the selected winner canopy, then we would destroy the complex mixture that we got. And there were hints in the literature now, or strong hints in the literature, that complex mixtures, the trees support each other and they grow rather better. So we thought, well, let's have a different policy. We'll halo pollard them. And the pollarding means that you can see here, the pollarding, that here's our chosen winner. Here's a Scots pine, and we've pollarded the surrounding trees at about 2 meters and above the lowest live ring of branches, so they all survive. And the targeted winner can then be in full canopy with all the support around it that you might get from mycorrhiza support or deep roots that bring hydraulic water up from the deep soils. And also the growing leaves on the pollards would chase the trunk up. We tend to prune the trunk. We want a nice big trunk. We want to make nice trees for the wood mill that we have at Norbury for planks and beams. But the surrounding halo pollarded trees would hide the trunk from sunlight and reduce the numbers of epicormic leaves that might appear. So that was our policy. The Forestry Commission wasn't sure about it. They hadn't heard about this before, so it wasn't terribly perhaps a good idea to ask them in the first place. And anyway, over the years, the trees have grown very well, and we have far more admirers of the trees now in terms of their growth rates, because the larch trees are 20 meters high, and the oak trees are 10 meters high. They're growing, we believe, at 2 or 3 times that we would see the normal growth rate of an oak in a pure oak plantation. So here we have, there's a nice hybrid larch, and then there's a poplar tree next to it, and some oaks over here, and this is a cherry tree. I've got to understand some of the differences over 13 years. And this was some sections of the trees that we cut. So let's just look at the one on the right first. This is a 33-year-old larch grown at Norbury in a plantation of pure larch. And on the right side here is a 12-year-old larch tree grown in our mixture. with halo pollardy. And you can see the growth rings are 3 times greater in our mixed culture, our mixed forest, which has been halo pollarded. The oak is also equally impressive in a slightly different way. Here's a 33-year-old oak from our plantations, and you can see that it's grown fairly similarly for a couple of years. And then when we thin it out and we halo pollard it, you can see the growth ring at year 10 and 11 are enormous. They're 4 or 5 times greater than the similar age growth rings on our pure oak plantation. By comparing this with growth rate in the Forestry Commission growth rate tables, you can see here how well they've done. So these are curves, reflect the amount of carbon storage. These are 4 tons per hectare per year in a hybrid larch in a rather poor soil condition over the 130 years of its lifetime. A really good soil or a really good growth rate larch might be 14 tons per hectare per year over its lifetime. And here's our trees. So we measured them. They're only young still, 13 years maximum age. You can see here it is. And expanded here, we can see that between the year 8 and 13, it's growing, accelerating its growth, and it's massively above the growth rates of all the plantations that have been measured by the Forestry Commission. And it's worth pointing out that in the Forestry Commission trees, they're all monocultures. The same is true for other trees in the mixtures. So here's a cherry. You can see it also has a huge growth rate, and even our humble English oaks are growing right at the top end of oak tree plantations that we see across the Forestry Commission. So why should that be? Well, it so happens that there have been a plethora of publications in very good journals since we made our first plantation. Our plantation is probably one of the oldest in the country that's got this great mixture that we've been measuring. But other experiments around the world in natural forests and in plantations show these growth rates are much better if you have a complex mixture. So this is a paper from the Science not so long ago. Productivity in mixtures, and this is cubic meters per hectare per year, we can call that tons, for over 750,000 natural woodlands. These are plots that are established around the world in all different sorts of forestry circumstances. And when they measure the tree species richness, and it's a percentage, because in the Amazon you have maybe 300 different species per hectare, but obviously in boreal forests you'll have far fewer numbers. But you can see, depending on the complexity, if there's a single species, you might get 3 tons per hectare per year, as we see in many forests in the UK, which are monocultures, up to this 12 tons per hectare per year. And this red line is one standard deviation. So it does appear that these mixtures are very important if we want to sequester carbon. How about experimentally? Well, it's the same. Here a nice paper in Science, more carbon storage with more species complexity in tree planting experiments. So here we have the first year of the planting, 1 species versus 24 species in a complex array of experiments. And if we have far more species, you can see by 2017, the growth rate has doubled in the complex mixture compared with a single species. Red maple. If you put red maple on its own, it will grow at this rate in the plantation. Put it next to some lime trees, again in complex experiments, it'll grow quicker. It doesn't like cedar next to it, but when there are 12 species in the mixture, then it grows at the greatest rate. This is nothing new. Charles Darwin noted in The Origin of Species by Natural Selection in 1859, chapter 4, page 88, and I've looked it up, it's true, that he noted that there was a 50% extra yield in grass mixtures if you had grass mixtures rather than if you measured the mean of the growth rates of the different species when they were individualized. So why? Well, we have tree canopy experts, we have soil experts, we have all sorts of experts, and they all claim it's their subject that describes the mechanism. So the canopy boys, Grossman et al. Says, well, 80% of it is due to the rugosity in the canopy. Here's the productivity in tons per hectare per year. 80%. And the rugosity means the amount of complexity in the canopy, the different leaf forms, different big ones, little ones. And so we can see that when we have a monoculture of spruce in Wales, or we have a complex mixture in the Amazon with 5 or 6 layers of trees interacting with the sunlight. And of course, if you have different species, then they interact with the sun at different times of the year. Conifer are always photosynthesizing. Understory trees photosynthesize a little more, whereas the deciduous canopy trees have a rather narrower photosynthesis time. The rhizal boys, the rhizosphere experts, say it's all to do with the roots. There are 1 million different species of fungi and bacteria in the roots, and the roots are far more complex in mixtures than they are in monocultures because they overlap. They occupy all different areas of the all different volumes of the roots of the ground. Deep roots will have hydraulic lift, supplying water to the shallow-rooted trees. They claim probably 80% as well. Then the pathologists, the Rob Jacksons of this world, say, well, it's all to do with what's the infection rates. And this is a paper in Science, and it shows that here's a plant diversity versus pathogen diversity. One species will have a certain number of pathogens. If you have lots of species, you'll have lots more pathogens. But overall, if you dilute the pathogens out with complex mixtures, and if you have 100 species in a mixture rather than a single species, the pathology is far less in these complex mixtures. And this is mostly in herbs. I'm sure it must apply also to forests. And we see that a little at Norbury, that this is a monoculture of Douglas fir, and it's infested with woolly aphids, Adelges coolei, and it's in a mixed forestry setting where around it are these complex mixtures. And the tree I've shown here, the leaves here, another Douglas fir, 10 meters away from this pure plantation with no woolly aphids on it. A more open structure to the woodland, but somehow the infection is enormously less. And one culprit might be that in the mixture, hormones, jasmoniums are released by trees that get attacked. These are released into the atmosphere, and they are telling ladybirds downwind that there are some bugs in our leaves, and they attract ladybirds, and we see many ladybirds on the trees in the open environment. Nitrogen shortage. We've seen from the BIFoR data that nitrogen may well be limiting. Post-glacial soils are normally nitrogen limited. And nitrogen fixing trees in our plantations will provide short and long-term nitrogen addition. There are 600 different nitrogen fixing trees in the world. There are 20 or 30 different species that will grow in the UK. These should be added to new plantations. The Forestry Commission should make a grab of it and put these nitrogen fixing trees into our growing young woodlands. And the analogy is that in our grasslands, we add 30% nitrogen fixing clovers to enhance the growth rate of the grasses. And there are many studies showing this. This is a paper from Canada showing that Douglas fir alone will grow at this rate. This is an 80-year experiment, But when you add red alder, which is a very strong nitrogen fixer, into the mixture, then you get nearly double the amount of stem mass over that period. So, in summary, trees in complex mixtures grow faster because there's more light trapping with complex canopies, different water and nutrient requirements, less infections to slow growth rates, and they should contain nitrogen-fixing trees. And then the management, we have special management, we have this halo pollarding, but we must control the grey squirrels. They're awful. They're destroying woodlands across the country. Their numbers are still increasing. They're pushing back the red squirrels into the periphery of the United Kingdom, Scotland and Wales. We trap them. We kill 600 to 800 per year. This year we've killed over 1,000. And if you don't kill them, they will eat the young buds and they will ring bark the trees when they get to 6 or 8 years old. And they've destroyed hundreds of acres, hectares of woodland across the country that have been planted with great expense by the Forestry Commission. Planting a tree is not the solution. You must look after it for the next 20 or 30 years. And deer, we mustn't forget deer. We have a strict deer control at Norbury. They get, if they're found trespassing, they're not warned off, they're shot. How many species should we plant? Well, we've got up to 30 in our mixtures. There are only 30 different species of normal trees of native UK trees. And the reason is of the ice ages. The horizontal mountains, Pyrenees, the Alps, Carpathians, have blocked the return of seeds from southern areas. The ice ages pushed all the trees south of these mountain ranges, and they've never come back fully. So in Europe, there are about 300 different species of trees, whereas in North America, where the mountains run north-south, the ice ages pushed the trees southwards, but they returned because the channels were still open. So there are 600 or 700 different species of trees in North America. And in China, where there are no significant land masses of that type, a barrier, there are 2,500 different temperate woodland trees. Why can't we plant a couple of thousand different species in England? If we waited 10 million years, there might well be 10,000 different species in the UK, like there are in the Amazon, 20,000 in the Amazon. The more species, the better. All the studies show that each extra species you add adds a little more carbon sequestration to that land. Faster growing trees. The foresters always say to me, you're growing them too quickly, they'll be weaker. Well, they're partly right. Conifer trees are probably weaker if they've grown very quickly. But ring porous trees, oaks, are stronger if you grow them quickly. The weakness is in the spring wood, where there's open xylem tubes. The summer wood has far smaller holes, and that's what increases with increasing growth rates. That's what sees this larger ring pattern, is the summer growth, and that has far lower, smaller pores, and it's stronger. When Nelson was ordering ships to fight the French, he ordered the oaks to be from fast-growing oak forests. They knew 200 years ago that oak was much stronger if it was growing quickly. And the diffuse porous, such alders, have similar holes in their rings throughout the year, and they stay with the same strength. But of course, if you've grown 3 times as much larch, the conifer, you've still got 3 times the amount of carbon capture. So, what's our score sheet? How have we done over these 13 years? Well, we did a big spreadsheet. We counted our carbon. We emit 700, and this is from 2020. We emitted 711 tons from our 3 biomass boilers, from tyre wear, from diesel tractors. Here's our average UK emitter, you guys, 13 tons per year. We've got about 18 tons of collateral absorption from solar panels, but our woodland has accumulated 3,000 tons nearly in the year 2020. Now soil, I'll come to that in a moment, we've also stored about 3,000 tonnes in our soils, in our arable lands, to give us a total of 5,000 tonnes per year of carbon storage at Norbury in 2020. This is much higher. I thought we might store 2,000 tonnes. So by carbon accounting, we've realised that we've done extremely well. The arable land we converted to mixed herbal lays, 23 species, the biggest range of species of herbal lays anywhere in the UK. Anywhere in the UK on these soils, these post-glacial soils. They have deep roots, they grow quickly, they don't get infected, and we bring the cows on, but they have mob grazing, all the cows, we're not taking silage, we're not taking the carbon or nitrogen away from the land, we're keeping it on the land, and the carbon storage is twice as much per hectare per year as it is in the woodlands. So, when we counted our carbon storage, we asked the people who were doing it to compare it with other estates, farms across the country. And here we are, here's our comparator. So these are carbon emissions on these farms, and these are carbon sequestration on these farms. And you can see that Norbury is storing 8.8 tonnes per hectare per year across the 600 hectares. Well out beyond all the other comparators, of which there were a couple of hundred. So complex mixed species forestry with active management could greatly increase carbon storage across the country in states and national parks in the UK. All landowners should have carbon evaluations as baselines, including the university, for carbon storage potential in woods, farmlands, and across the estates. Thank you.
Ask myself and Jenny to come. Jason, do you want to come? Claire, if we could have you, if you could extricate yourself from the... Did you know you were going to be asked to come down? Oh, good. But you still decided to sit in the middle of the auditorium. Well, no, that's fantastic. And I'm going to, when Claire takes her seat, I'm going to give her the opportunity to say a few words, although we've heard something about her work through Jenny's talk. I think it's only fair, since we haven't heard from you, we'll hear from you tomorrow. But if you wanted to just say a couple of sentences about your work. So Claire is a professor at the University of Exeter with an expertise in wildfire.
Yeah, that's right. So I work on wildfires. I started my passion for wildfires in deep time, including working with Jenny, but I've become much more interested in looking at how evolutionary adaptations in plants can impact the past and through to future, and also do a lot of work on the flammability of UK ecosystems now as well.
Thank you very much, Claire. And I think that's going to come in as we draw together. I'm going to try and draw together and draw on questions. So please, anyone who's still got their laptop working and anyone online, please feel free to keep putting questions into the Padlet. But I think I'm going to try and draw together some of the threads that we heard from Jenny and from Joe, especially around structural complexity of forests and what that gains for us, where the difficulties might be. And I think fire is obviously going to be one of those catastrophic resets, perhaps. We need to hear a little bit more about that. But let me start by just picking up a question from the Padlet. We'll start with you, Jenny, if that's all right, because I think it was aimed originally at you, which was about which tree species might be best able to adapt and take us forward currently.
The million-dollar question. That's really difficult. So I didn't get a chance to talk about a lot of our modern work, but we have looked in different biomes, forested biomes around the world. And we looked at their response to the last 50 years of climate change. That's on a very small scale. And what we saw, a clear pattern of plants, evergreens are doing much better under increasing CO2. We also see the same pattern in the fossil record. And why is this? Well, we think it's because they are using water more wisely. So they have a higher water use efficiency gain under elevated CO2, more than their deciduous counterparts. So if I was to make a recommendation, I would say we absolutely can't beat the mixture, because we don't know, you know, the greater the number of species present in the forest, as we've seen from Joe's talk, but definitely have a mix of evergreens and deciduous.